Hello everyone, it's a great honor that we have this opportunity to make the presentation to share our solution named Attention-Based Knowledge Chasing with Rich Interaction Representation on the AAAI 2023 Global Knowledge Chasing Challenge. Our team name is KeyCoin at USTC, and these are our members. My name is Bihan. We start our presentation following the four aspects. First of all, we are going to introduce the background and task of this challenge. Then we will introduce our data analysis and the solution for the challenge. Finally, we will show the results of our solution. Knowledge chasing is the task of using students' historical learning interaction data to model their knowledge mastery over time so as to make predictions on their future interaction performance. By accurately estimating students' knowledge proficiency, students can better realize their weakness and improve learning efficiency. The statistics of the challenge data set is shown in this table. The data set is made up of 18,066 students, 7,652 questions, and so on. The evaluation task description is here. There are 3,613 student interaction sequences in the test set. For each interaction sequence, the first 50% of interactions are no, and the task is to predict the rest 50% interactions responses. The input is formalized as students' historical interactions, each of which is composed of user ID, question ID, knowledge concept ID, and time steps. And the output is prediction results of students' future performance. Then we present our data analysis of the dataset. First, we analyze the distribution of students' interaction sequence length, and the longest is 1028, as we use the 50% of interaction sequence to predict the left ones. We set all input sequences to a fixed length as 550. For the shorter ones, 0 vectors are used to pattern them up to the fixed length. Each question is associated with question type, question text content, question analysis, and its corresponding knowledge concepts. We analyze the top 10 most frequent words in the question content and analysis, and finalize the anonymized word token. 832 appears most of times, which is possibly referring to some meaningless words like blank space. We use question content and analysis length to enrich the question representation and remove the top 3 most frequent word tokens. Considering that the analysis length of question reflects question's difficulty to some extent. For example, a difficult question is possibly accompanied with longer analysis. So we first compute the average length of all the questions analysis, and then represent the relative analysis length as 1/3 of the average length, or 2/3, or the other. Although the dataset descriptions illustrate that there are 3 types three types of questions. We find the dataset only holds two types, as blank filling question and the single choice question. The question-related knowledge concepts are hierarchically structured, and there are 1175 concepts at all, and 10 root concepts in the tree-like KC structure. We further analyze the 10 distributions of each interaction's interval 10 with its last and next interactions, and use 10,000 seconds as the basic unit for discretization in the training phase. Then we begin to introduce the solution we use. In addition to the basic question-answer pair, we enrich an interaction with question type, question analysis length and relative length, question content length, question-related knowledge concept, and root of concept path in the hierarchical KC tree. Intervals with previous 8 interactions and the intervals with future 8 interactions. The number of stars is related to their importance, and by adding the interval 10 of an interaction with its previous 8 interactions and the future 8 interactions, improve the performance of our solution most. After obtaining the enriched interaction representation, we use the cross-attention mechanism to compute the student's knowledge state at each time step. First, we project the historical interactions into the query vectors, while projecting the predicting interactions into the key vectors and the value vectors. Then we compute the dot product attention values between the query vector at j time step with all the key vectors, and apply the attention weights on the value vectors. Finally, we incorporate the weighted sum of value vectors with the original interaction embedding to form the student's knowledge state at time step j. And the performance is improved using the cross-attention mechanism compared with the linear layer by 0.15%. As students' future performance on a specific question is closely associated with their past responses on similar questions, we first compute the attention weights between predicted question EI with historical ones through the softmax function fitting question similarity. Then, noting that the student's proficiency is reflected better in the recent interactions, so we use position-aware weights redistribution strategy to give larger weights on the closer interactions as follows. We compute the position weights of each interaction as beta 1 and beta 2. Noting that through adding the beta 1 and subtracting the beta 2, we move part of the attention value from the front interactions to the late ones, and the total value of the dot product attention is still kept as 1. Finally, we apply the redistributed attention weights on students' historical knowledge dates and obtain the weighted sum vector to predict students' performance on question EI. The utilization of the weight redistribution improved the performance by 0.005%. We achieve data augmentation in training phase by setting the split ratio of historical sequence and predicting sequence randomly in 40% to 53% instead of the strict 50%, and thus introducing variability into training data distribution, and the performance is improved by 0.1% with strict split strategy. We set up the training process 20 times by randomly splitting the dataset in a 9:1 ratio to obtain the training set and validation set, and take the average at final results. Our team win the first place in the competition with the AUC score at 0.8178 in predicting students' future performance. In fact, by repeating training process 5 times, the AUC score can achieve 0.8176. Our code is publicly available at GitHub, seeing this link for everyone to follow. If researchers want to learn more about knowledge chasing, this paper can provide good guidance. That's all for our sharing, and thanks to everyone for listening.